Hey everyone, I'm Anish and welcome back to PrepFusion. So today we'll start the lecture 9 of Bode plots. So previously we learned about second order Bode plots for second order systems for complex conjugate roots. So that wasn't just covered. So how to approximate for complex conjugate roots we understood. Basically we convert it into critical damped only. So like basically the poles are at omega n, so corner frequency is at omega n. So definitely there is some error, and due to that we get huge amount of error in the approximate plot and the error actual plot. So we learned about that. So I left you with one of the questions. So we have been given a transfer function, and the value they have asked us to find the values of constant gain term and the highest corner frequency of the Bode plot. So what is the constant gain term here? So constant gain term, they mean by constant gain term is this k term, but here like this is not in time constant format. So definitely this 5 is not equals to my constant gain term. So in the option also 5 is not given, like this 5 is for the highest corner frequency, not for the constant gain term. So first thing what you should keep in mind is k is this constant gain term, k is not equal to 5. Okay, why? Because transfer function not given in time constant format. Okay, this is the first thing. So we have to convert it into time constant format. So let's convert it. But before that, what other thing can you notice? Like they have asked for the highest corner frequency. So for finding the highest corner frequency, obviously you will need the location of the poles. So here, what is the location of the pole? 0.25. Here the pole location is 0. So obviously these two are there, but we have to check the location of the poles here. Okay, so check location of poles. Now what you can do is, what you find here is that like whenever this type of format is given, like s square plus a s plus something, okay, some constant number, then you always check whether the roots are complex conjugate or not. How do you check that? Basically you check the discriminant of this quadratic equation. So just by seeing this you can do this, you don't need to write anything. What you do, b square minus 4ac should be greater than 0 for it to have real and distinct roots. It can have equal also if this is like b square minus 4ac equals to 0. Okay, let's see. So b square is 4 minus 4ac minus 100. Sorry, b square is 16 minus 100, which is something negative, minus 84. So under root of negative 84 will be something imaginary, so you will get complex conjugate root. So here, like just by seeing that, I'm seeing that this we get complex conjugate root. Okay, we get complex conjugate root. And what are the real part? The real part will be minus b upon a, which is minus 4 itself, so real part will be on the minus 4. Okay, so here this one 4s plus 25, the discriminant, like this is equals to 0, so the discriminant d equals to b square minus 4ac. Okay, so what is this equals to? This is simply equals to 60 minus 100, simply equals to minus 84. Okay, minus 84. So the discriminant is equals to minus 84. So definitely, like from here we can understand we will get complex conjugate roots. So whenever complex conjugate roots, let me write this. Conjugate roots. So and like so what we'll do, we'll assume like the this format should be this, that it should be s square plus 2 zeta omega ns plus omega n. Then what we do, whenever we get complex conjugate root, then assume corner frequency at omega n. So here I'm assuming corner frequency at omega n and slope after omega n equals to minus 40 dB per decade. Okay, equals to minus 40 dB per decade. So slope after omega n is equals to minus 40 dB per decade. Now this is about the omega n, right? So now what you can do is you can simply take common omega n and like then what will be my corner frequency, highest corner frequency? So sorry, this is I have to do one thing, sorry. Yeah, so what is omega n square here? Omega n square here is 25, right? Omega n square is 25 because this format is matching. Okay, coefficient of s square should be 1 to keep this in mind. So and this is 25 and omega n equals to 5 itself. Okay, so omega n equals to 5 itself. Okay, so these are the things. Now what else? So basically omega n we got. So this is the highest corner frequency from here. So 5 will be the highest corner frequency. So either option A or option D will be correct. These options are eliminated. So now what about my k, value of k? So for value of k, what you can do? Simply take what we used to do. We should take common the omega n itself. Omega n we should take common. Okay. So from the equation, okay, where is the equation is not present? So what I will do? This is 5. So now we'll convert g of s into time constant format. G of s into standard time constant format. Okay, so what do we do here? So basically so we have 5 over here, and also like I have to take common s4, right? I have to take common 4 here, take common 4 over here. So this will be times 4 s by 4 plus 1 divided by s into 0.25 into s divided by 0.25 plus 1. Now what do we do? Here we take omega n square common. If you remember, we normally say omega n square. So we'll take common as omega n square. (25) common, and this will be s square divided by 25 plus 4 by 25, and this will be 1. Okay, this is how we convert it, if you remember correctly. So now just simply like what we will do, this 5 will get cancelled with this, so we'll have 5 here, and this is 1 by 4. 4 will get 4 will get in the numerator. So this is 16 by 5 itself. So what do you get? This is 3.2. Okay, and this is equals to k. It's k, right? So I will just copy this. Equals to k. So this is equals to k. So basically this is equals to k, right? This is equals to k. So like one more thing. So 3.2. So what is the option? 3.2 and 5. So option A is correct. Okay, option A is correct. So I should write here like my corner frequency. Like I assume corner frequency is here. Okay. So basically how, like any other method, like without the discriminant, can you do it? So basically what you could have done is you could have found the zeta also. Okay, you compared this with that equation, you found out omega, and like you assume that you have got complex conjugate roots. You write omega n square, then you write then you find like zeta. then you find zeta. So how will zeta look like? No, you need to assume complex conjugate poles. This is valid for all of them, right? This is valid for all of the type of second order system. So you just compare this with omega n square, and then you put omega n in this equation. So 2 zeta omega n equals to what? 4. Equals to 4. So now if you put this equals to 4, your zeta will be, so this omega n is 5, so 10.4, zeta is 0.4. That means my zeta is 0.4. That means it is lying between 0 to 1. That means I have complex conjugate poles. Complex conjugate poles. Okay. So yeah, this is the question basically. So let's swiftly move to the this question, this lecture. Basically this is same, only I forgot to tell you that here in this lecture also we'll do mainly questions. Okay, mainly whatever we have studied till now, we'll just revise. So this is a very interesting question, recent question, gate 2016. Either you can do it in seconds, or it will take you very high time if you don't know about the concept of Bode phase plot. So here we have been given an asymptotic Bode phase plot. Okay, and this is written like k by s plus 0.1, s plus 10, s plus p1. Fine. With k and p1 both positive. K and p1 are both positive. Okay, they want us to find the value of p1. How will you find the value of p1? So what we have to notice is that two roots are given, two poles are given. Okay, one is we have to find out. So if this is given, okay, we don't care about the k term, okay, and don't care about the constant time constant format, because we are not plotting the Bode gain plot. We are concerned with the Bode phase plot. So in that we don't care about the gain and stuff. So we are only concerned with the corner frequencies. Okay, so here we have a pole at s equals to 0.1. What does this means? This means 10 times before 0.1 and 10 times after 0.1, the slope should be minus 45 degree per decade. So 10 times before 0.1 is the slope minus 45 degree per decade. Here if I see, I am moving from 0.01 to 1, moving 45 degrees. That means in 1 decade I am traveling minus 45 degrees. So it is minus 45 degrees per decade. What does, so this is satisfying. What about this? 10 times after this should also be minus 45 degree per decade, but from the line itself, from the slope itself, we are seeing that slope is further increasing in the negative direction. That means it is not minus 45 degree per decade, but still we can cross verify. In 1 decade, okay, from 0.1 to 1, it is traveling from minus 45 to minus 135. That means it is traveling to minus 90 degrees. So in 1 decade it is traveling 90 degrees. 1 decade traveling 90 degrees. Okay, so yeah, that means what is the slope? Slope is minus 90 degree per decade. But should it be 90 degree per decade if only this pole was like present around this region? It should be minus 45 degree per decade, but it is minus 90. So definitely something has changed. Some pole has been introduced because the slope has further decreased. Okay, also let's check for s equals to 10. Now at s equals to 10, 10 times after this and 10 times before this, the slope should be minus 45 degree per decade, only due to this pole I am talking about. Okay, so 10 times after this, my slope is here I am going 1 decade, and in the y-axis I am traveling minus 45. That means, okay, 10 times after this I am getting minus 45 degree per decade. That means like this slope is only influenced due to this pole. So in this region I have only this pole. That is what this slope is telling me. But if I travel from 1 to 10, again my slope becomes minus 90. You see, okay, 1 decade I am traveling, and I am traveling 90 degrees in the negative direction. So my slope is minus 90 degree per decade again. So what is this telling me? This region is telling me I have another pole around here. I have another pole around this region, which is contributing to further minus 45 degree per decade slope. So this is contributing minus 45 degree per decade, but another pole is there somewhere in this region which is contributing another 45 degree per decade. Where is the pole? Now either you can guess, or you have understood by now that this 1 decade and this 1 decade is total 2 decades, and this two decades my slope is further getting reduced by 45 degrees. That means between these 2 decades here I will have another pole. If I have another pole here, now if I travel from 0.1 to 1, this pole will contribute minus 45 degree per decade, and this pole will also contribute minus 45 per degree decade in this region. Now I am around here. Okay, around here, and like if I travel from here to here, if I have pole here, so this pole is contributing minus 45 degree per decade, and this pole is also contributing minus 45 degree per decade. So definitely this is minus 90 degree per decade. So definitely I have a pole at 1, so definitely P will be 1, because nothing else points are given, right? No other points are given anyways, but still, like from here you can understand intuitively that my pole will be 1 radian per second, P1 will be 1 radian per second. So this is just by seeing the question. You can solve this just by seeing the question. Now if you don't want to solve this just by seeing the question, now let's write things down. So now what do you observe is that observations but okay. So what observation I see? So like I have a pole here, omega P1. So this is, what is this? Oh, this is P1. Okay, so let me name this as omega P2. Pole 0 point, like this pole will affect till 0.01 to 1. Okay, that is the range of this pole, due to which what slope I will get? I will get minus 45 degree per decade. Okay, and due to this, like the this pole, this will be 1 to omega P3 100. This will be another minus 45 degree per decade. Okay, so these are the ranges. Now obviously in the graph, what I am seeing, in the graph I am seeing that my slope is, like before this 0.01 it is 0. Okay, hence before this 0.01 it is 0. So obviously this P2 is the minimum pole. Okay, minimum pole. And after, between this 0.01 to 0.1, my slope is between 0.01 to 0.1, my slope is minus 45 degree per decade. That is fine. So this range is matching. Okay, this range is matching. But after this, what is happening? After the 0.1 to omega to how much? To almost 10. Almost 10. Okay, not almost 10, exactly 10. My slope is minus 90 degree per decade. Okay, so this is my slope. Okay, this is my slope. Now what does this mean? This means I have a pole around here, right, like which is getting affected by 0.1. So since 0.1 the pole is getting active, so obviously if the pole is getting active here 0.1, obviously 10 times after this my actual pole will lie, because the slope gets activated 10 times before that. So pole will lie 10 times after this. Okay, and like from this also you will understand that 1 to 100 it is telling me minus 45, but I am going till 10 minus 90. So obviously like between 1 to 10, between 1 to 10 I'm getting minus 90. That means that 10 times before this 10 I have a pole here. Okay, 10 times before this and 10 times after this, because just here my pole, like slope reduces from minus 90 to 45. That means the pole gets deactivated, the effect of pole gets vanished. So just after this effect of pole gets vanished, so 10 times before this my pole will lie. So yeah, this you can understand. So I'm not explaining it further. So like from here we can understand. Let me just write after 0.1 radian per second, the effect, the slope reduces further by minus 45 degree per decade. That means there is a pole at 0.1 times 10, which is radian per second, 1 radian per second. Okay. Now just this is the same thing. Just what we'll do, what we'll write is after 10 radian per second, the slope reduces increases further. The slope increases further by plus whatever degree per decade. Actually this should be per decade. Okay, so 45 degree per decade. So this is the case. So here what does this mean? There is a pole at 10 times before 1 radian, this 10 radian per second, right? So 10 times before this. Now luckily both of them come at the same location, or else there would have been like the calculation would have been difficult, definitely. So yeah, 10 they will give some easy calculation only. So obviously from these two cases I can cross verify that my pole omega p1 will be equals to 1. P1 will be equals to 1. Okay, don't write P1 as minus 1 because they have already given what P1 is as plus P1 they have given. If they would have given as minus P1, then you would have written P1 equals to minus 1. Just be careful. So P1 will be equals to 1. Okay, so yeah, this is my answer for this question. Okay, so now let's go to the next question. What is the next question? So here we have the question that the asymptotic Bode plot of transfer function of k divided by 1 plus s plus a is given in the figure. The error in phase angle and dB gain at frequency of 0.5 e. Okay, so this time like this is the asymptotic Bode, but they have already given it. Although you could have drawn it by yourself, but they have given it. But they want you to find the error at 0.5 a, not at corner frequency, not at corner frequency. They want you to find the error at 0.5 a here, somewhere around here. Okay, so obviously error for phase won't be 0. Okay, and error for this won't be simply minus 3 into n, because what is happening here, they haven't told us to find for corner frequency. So that's why I generally don't recommend mugging a formula, because if you just mug a formula that yeah, error for this gain plot is minus 3 into n, error for this phase plot is 0, but that is at the corner frequency. But they have they asked at the corner frequency? No, they have asked some frequency which is not equals to corner frequency. So keep this in mind. So omega equals to phi not corner frequency. Okay, so yeah, So like then what is my what is my error? Error is actual minus approximate value. Okay, so let's write this down, or what we used to do. Yeah, it was actual minus approximate value, or I forgot like what we used to define like the error. Was it approximated minus actual, or what was it? I written it here, right? Yeah, actual minus approximate. Let's see like the previous where I was defining my error. Was there something wrong? Yeah, here actual minus approximate, so I was correct. Okay, so it is actual minus approximate. If it is actual minus approximate, okay. So obviously like what is the actual value? So actual value, you just you have been given the transfer function, you just simply write it like that, g of j omega. They want us to find in, okay, they want us to find in dB, so we'll obviously convert everything in dBs. Omega equals to 0.5 a, this is k by under uh, omega by a square plus 1. Okay, now this is like you put 0.5 a here, this is 0.25 plus 1 under root. Okay, so now you convert it into dBs. So if you want to convert it into dBs, so obviously what will happen, this is ratio of two numbers, so this is 20 log k minus, now this is like power half, so what you can do is like this is 20 log under root 1.25. okay, so basically like the value of this, let me calculate this one, 1.25 under root and log into 20 is almost 0.97. okay, so this will be basically the error. So this is 20 log k minus 0.97. okay, so this is minus 0.97, and now what is the approximate value? What is the approximate value? So approximate value you can see from the graph itself, or you know already, like before corner frequency this will be constant, like this is 20 log k simply. So g of approximated g omega at omega equals to 0.5. okay, so iske like sorry, I was just talking Hindi. Then what my approximate value, it is 20 log k. okay, base 10 is there. okay, I'm not writing base 10. So like let's find the error in dBs. okay, will be simply this this one subtracted by the other one, so this is here. okay, so this will be equals to minus 0.97 dBs. okay, so this is my error, this is my error. okay, this is my error. Now like in the option, like let's say in the option if plus 0.97 is given, obviously you will tick that. okay, if minus 9.97 is not given and only plus 0.97 is given, you can tick that. okay, just check if it is not MSQ or something. If it is simple MCQ, yeah, you can tick that. But sometimes what they happen, they just want to know the magnitude of the error or something, right? That's why like this sign doesn't matter to them much. Sometimes happens like if negative isn't there in the options in MCQ, then you tick plus 0.97. Now let's find the error in phase angle. So error in phase, again let's write the angle like angle formula. It is simple, right? Tan inverse minus tan inverse omega by A. So what is this? 0.5, so minus tan inverse 0.5. Okay, like this is at omega equals to omega 0.5A. So 0.5 tan inverse. Okay, what? Yeah, this is in degrees. What am I doing? Something wrong? Something is wrong. 0.5. Yeah, 26 point. I told you guys to remember. Okay, this formula I told you guys to remember. Like tan inverse 2 and tan inverse 1 by 2. They're just simply 90 minus of each other. So this will be minus 26.56 degrees. Okay, now let's find the angle here. Now the angle isn't simple anymore. Why? Because this is changing and I have to find in between. Okay, so like we can use the formula as this is not simple linear scale. We just simply can't use that y equals to mx formula. That we can't use. Okay, just be careful. This is not a linear scale. So we have to use that slope formula in the log scale. Okay, in the log scale we have to use. Okay, so in the log scale if you use, what will happen? So what is this value? This is like minus 90 because it is going from 0 to 2 decades, so it will be minus 90 here, but we don't care about that. We know this is 0 degrees. They haven't mentioned it, but they should, like, this is 0 degrees. Okay, this is 0 degrees. This is important. So now what you do is 0 degrees, you simply use the slope formula. So let me mark few points here. This is A and this is B. So slope A comma B equals to yb minus ya divided by log of omega b by omega b by omega a. Okay, so like yb we have to find out here. And this b location is at 0.5a. So yb definitely we have to find out. So this is yb minus ya is 0 and this is log of, again this is like 0.5a2 divided by 0.1a, so which is log of 5 itself. 5, base is 10 and slope is minus 45. So minus 45 into log base 10 of 5 equals to my yb, because ya is 0. So this is equals to my approximated angle g of j omega at omega equals to 0.5a. Okay, so basically what is happening over here? So basically my angle of g of j omega at omega equals to 0.5 equals to, like, what is log 5? Log 5 is 0.69 times minus 45, simply equals to minus 31. Okay, pretty close, but still there is some error. Minus 31.4536 degrees. Okay, so this is my log 5 basically. So this is the value of approximate value. So what is the error? Basically? So error equals to actual 26, like this is minus 26 minus 26.56 minus of 31.4536. So what is this equals to? Plus, okay, 26.56 almost equals to 4.9. okay, almost equals to 4.9 degrees. So my answer will be 4.9 here. Okay, so yeah, my answer will be this 4.9 degrees. This is the first second answer, and this is the this answer. Okay, two answers, 4.9 degrees and 0.97 degrees. Okay, so yeah, these are the two answers basically. So this is it for this question. Let's move on to the next question. So let's see this question. This is also a a gate question, but I have forgotten to write the year. So here what does this tell us? So here they have given us the gain and the phase angle. They have given us the gain and the phase angle of a stable transfer function. The Bode magnitude and phase plot of a stable transfer function is given. They haven't told us about anything about the coefficients of S or something. They have given this, that consider the negative unity feedback configuration with gain k. This is the negative unity feedback configuration in the feed forward path. Fine. The closed loop is stable for what value? Okay, is stable for what value? The maximum value of k naught is what? So here what do you observe is that currently what are, they haven't given us anything here, they haven't given us anything here, everything no, only this graph is given and few information in the graph is given. So obviously we'll decode few information from the graph itself. Okay, so information from graph. Okay, obviously you will do this much faster when you know which information to take and which information to ignore, but for now we don't know which information to take and ignore. After solving this question, after solving many questions, you will understand which ones to ignore and which ones to take. Okay, information from graph. So here if you see that what is the information here, the information here is they have given us the phase at this particular frequency, and the same frequency they have given us a gain. And what is the phase here? Phase is minus 180. So if you know the phase here, what is this called? Like when at what frequency is my phase minus 180? It is the phase crossover frequency. So at omega pc they have given me the gain, but they haven't given me the omega pc, but they have given me the gain at phase crossover frequency. So okay, what is it? It is equals to 20 dBs. It is equals to 20 dBs. Okay, what else they have given me? So here they haven't provided me the frequency at which the function reaches 0 dBs, or it is also known as the gain crossover frequency. They haven't provided me. Also they haven't provided me the phase also. So okay, where did it go? They also haven't provided me the phase also. Okay, so yeah, we'll obviously we don't know that. Now what else they have provided me? They have provided me the DC gain also, because they have provided me the low frequency gain, which we'll assume as DC gain, because we don't have any poles or zero at the origin. So provided me the low frequency gain, frequency region gain, as no poles and origin are present. Okay, that means it will be simply equal to DC gain. Okay, DC gain, so which is simply equals to n naught by d naught. Okay, you put g of s equals to 0 over here, so obviously all this will get cancelled, only n naught by d naught will be remained. So this is equals to what? This is an absolute scale and they have provided us in dB scale. Okay, so dB scale is 36 dBs. 36 dBs. Now you convert this into absolute scale. Okay, simple equals to 20 by 36 is to 1.8, which is 10 raised to power 1.8. So it is 1.8 itself. Okay, 1.8. Okay, so it is 10 raised to power 1.8. So n naught by d naught is 10 raised to power 1.8. Now is this information even useful? We will see. 10 raised to power 1.8. Okay, now what is this value? Let me calculate this. It is 63 63.1. Okay, it is 63.1. So n naught by d naught equals to 63.1. Okay, so these are the two information that I know from the graph. Now what they are telling us is to find the maximum value of k naught for which system is stable. Now is the system stable right now? Is the system stable right now? So here how can you identify if the system is stable or not? So what you can do is that, what is this frequency called? Phase crossover frequency. You put phase omega pc over here. Okay, omega pc over here and omega gc over here. Okay, now I told you one condition, right? If you recall correctly, that your phase crossover frequency should come later for stability. Okay, your phase crossover frequency should come later for stability. Like phase your omega pc should be greater than omega gc. Okay, this was one condition for stability. Okay, for stability your omega pc must be greater than omega gc. Okay, so is it the case here? It isn't the case. Like from here I can understand that my system is unstable. Currently it is unstable, but with the variation of k I can make it stable. But is this true really? Let's check. So let's check the gain margin right now. So we know the gain at this. So what is the gain margin? The gain margin is simply equals to 1 by magnitude of this transfer function omega pc, which is in dBs, it is in terms of like minus magnitude of g omega equals to omega pc in dBs. This is in dBs. So like what is this currently? Currently this is 20. So my gain margin equals to minus 20 dBs. Now what we know in dBs for stability, my gain margin should be greater than 0, which is not the case here. It is less than 0. So definitely it is unstable. Currently unstable. But we want to make it stable. How to make it stable? So what I am doing is, what is this doing? Simply multiplying k with this magnitude. Okay, k is real. Okay, so simply multiplying k with this magnitude. So obviously this one will become k over here, k times this. So my gm currently will be simply magnitude of k, g of j omega equals to omega pc. Okay, so now like in terms of log, how can I write it? In terms of log, this will be simply minus 20 log k. K will come outside. Okay, because k is real and positive, k will come outside. Minus 20 log k, and the same thing only. Like what is this value? This value is this. Okay, and this is in 20 dBs. This is 20 dBs. Okay, this we know from the graph. So this is 20 dBs. And this is also in dBs. I won't write dB anymore. From graph. Okay, so now this is this. So what happens over here? So for this has to be positive. For my system to be stable. Okay, so obviously this has to be greater than 0 for stability. Minus 20 log k minus 20 should be greater than 0 itself. So obviously log 10 base k should be greater than minus 1 here. So this equation becomes k should be greater than 10 raised to a minus 1, which is k should be, okay, what did I do wrong here? Just what to say, k should be greater than 0. Okay. Yeah, I was doing the silliest mistake in inequalities. Actually here we have to take care. What we have to take care is, like, never just divide by something which is negative. In the inequality case, what happens? The sign of inequality changes. So I was also forgetting the same. So here, like, just shift this minus 20 over here. Okay, minus 20 log of k greater than 20 itself. Okay, fine. Now this is fine. But what else you do? Now you don't divide by minus 20, you multiply by minus 1 by 20 on both sides. Now if you multiply by minus 1 by 20 on both sides, you're multiplying by something negative, so the sign of inequality will change. So very important step, that multiply this equation with minus 1 by 20. So here sign of inequality will change. Okay, so obviously this one will become like log of 10k will be less than minus 1. Okay, because we're multiplying by something negative, so sign of inequality will change here. So this is 10 raised to k should be less than equals to 10 raised to power minus 1, so k should be less than equals to 0.1. Okay, so this is equals to my k naught, this is equals to my answer, this is equals to my k naught. Okay, so this is how you can do it. Or what you can do is, like, you convert this into absolute values, then you do that. Okay, how to do this in absolute values? So this is in dB scale, so k will be equals to 0.1. This is the answer, so 0.1 will be answer. Okay, 0.1 will be answer. Now let's do this in, like, this is in dB scale, let's do this in absolute like a decimal scale. Same thing only, right? Just for the people who don't who are a bit confused in the dB scale, they can, like, try this one out also. So in absolute scale, so what is happening? Magnitude of g of j omega at omega p, we know omega equals to omega p, we already know. What is it? It is simply equals to 20 dBs. Okay, and what is the absolute form of 20 dBs? It is what? 1, because, like, 20 divided by 20, like, it is actually equals to what? 20 divided by 20, 10 raised to power this, so this is 10 itself. So obviously this is equals to, sorry, this is not 1, so this is 10, this is 10. Okay, so this will be equals to 10. Okay, in absolute terms. Now like, what is my this magnitude of k times g of j omega at omega equals to omega p? It is 10k simply. Okay, now what is the gain margin? Gain margin is simply 1 by magnitude of g of j omega at omega equals to omega p, or omega pc you can say. Okay, omega pc you can say, whatever. So this is equals to 0.1 by k. Okay, so yeah, this is this. Now, like, just 10k, so this has to be greater than 1. Now this is an absolute scale, so this has to be greater than 1 for stability, so here, right, we don't have any negative ka chakkar. So yeah, this is, like, one good thing about this. So, like, you can cross verify if you want. Okay, so so my k will be simply less than 0.1, directly you can get from the absolute value. Okay, so, like, here we didn't need this information, the n naught by d naught. Okay, in some questions it may be needed, it may not be needed. Okay, now slowly by solving questions only you will understand when, like, you need to write this or you don't need to write this. Okay, slowly by solving questions you will understand. So yeah, this is the, like, from this is the two methods you can do with absolute scale, also with dB scale. Also dB scale, the problem of negative comes up because everything is in algebraic sums, but in absolute scale, like, it is in multiplication, so obviously the inequality, like, that problem won't come, so that is why. So yeah, that is one thing. Now let's solve this question. This is the last question of Bode plots basically. So here the transfer function, we have to find the transfer function from the Bode plot. So this is the first question, and find the, so I should write, like, find the find the transfer function from the given Bode plot, magnitude plot, and find the error at the corner frequency. So to find the error at the corner frequency. So here, like, what is the corner frequency here? Do recall? Is the slope changing over here? No. The slope, is the slope changing over here? No. Even like the frequency is also not given. So corner frequency is here only. Slope is changing over. We have to find the error for this corner frequency and the magnitude. Now, as zeta is given, so the error formula will be different here. The error formula will be different here. Do keep that in mind. So zeta is given, the error formula is different. Okay, like we are observing that suddenly my slope is changing from 20 dB per decade to minus 20 dB per decade. Okay, so minus 40 dB per decade, 2 poles at this corner frequency. So zeta based system, second order zeta based system, simple. But what other thing I'm noticing, like what to find the transfer function. That's why I'm telling you all this, that I have a 0 at the origin also. Initially my slope is plus 20 dB per decade. So initial slope is plus 20 dB per decade. Okay, initial slope is plus 20 dB per decade, and after this corner frequency it becomes minus 20 dB per decade. Okay, so like corner frequency zeta based system, so is 2 radian per second, and from here we can find the information about omega n. Omega n is 4. Okay, sorry, yeah, omega n is 2 itself. Sorry, omega n is 2 itself. So because like for zeta based system, omega n is corner frequency itself. So this is one thing. Okay, initial slope is there. So like initially, like I will have something like this, ks, fine. Okay, then due to this, like the slope is minus 40 dB, like slope change in slope, delta slope per decade. Okay, okay, so my slope is minus 40 dB per decade. So this is the slope. Now like can we approximate it? Like what is the order? So zeta they have given 0.6. So obviously I can write the characteristics equation from this. So it will be s square plus 2 zeta 0.6 into omega n 2 s plus omega n square 4. So this is s square plus 2.4 s plus 4. So this is one of the like terms, and this is one of the terms, and yeah, these are the only terms. Okay, so like let's write the transfer function. So obviously the transfer function k times s. So let me write this in better format. So this is like, let me write this in the time constant format. So this will be s square divided by 4 plus 0.6 s plus 1 equals to 0. So if I write this in time constant format, s square plus 4 okay, this is equals to 0.6 plus 1. Okay, so yeah, now like what is the value of k over here? What is the value of k? So the value of k you can understand from here, right? 0.1 they have given me the gain. Okay, so simply the magnitude of j omega at omega equals to 0.1 is minus 20 dB. Like minus 20 dB is what? Minus 10. Okay, sorry, minus 1 by 10. 1 by 10. Okay, like let me write here minus 20 dB, that means 10 raised to power minus 1 simply. Okay, so like what is this expression? So obviously this s will come here, but this can get ignored because like 0.1. So 0.1 whole square, like what we're doing, magnitude, right? So this is 0.6 into 0.1 whole square, and this one also. So like we're squaring, so these are getting ignored, you know. So put s equals j omega and write the magnitude expression and put 0.1. You will see that all these are getting ignored, only one is getting left out. So we'll get k will be equals to 0.1, like k into s is like k into j omega, magnitude is k into omega. So 0.1 divided by 1 will be equals to 0.1. So my k will be equals to 1 itself. K will be 1 itself. So my value of k is 1. Now, like we got the transfer function. So we got the transfer function. Transfer function equals to simply s by s square divided by 4 plus 0.6s plus 1. Okay. So this is my transfer function. Okay, this is my transfer function. So this is done. Now what about my like error? What about my error? So error simply is what error is simply minus 20 log of 2 zeta. Like if you want to remember the formula, you can remember, or you can derive from the basics. I have derived from the basics also. Okay, so error equals to minus 20 log of 2 zeta. So what is the error? So minus 20 log of so what is zeta? Zeta is 0.6. So 2 times 0.6 is 1.2. 1.2, which is equals to what? 1.2 log into 20. Okay, which is equals to minus 1.58 dBs. Okay, so this is my error. So you can either write this, or in the previous lecture we derived the from the basics also. You can do from the basics also. So here if we just go back here, here right, we derive from the basics. The DC gain was k equals to 1, so that's why. Else the error would be like even though like k term anyways gets cancelled, so error will be this minus 22 zeta. Okay, so yeah, you can directly write this, or you can plot this over here. You can do this over here, whatever you wish to do, right? So yeah, you like if you put omega n here, that's why like you're only remained with this, and magnitude becomes k by 2 zeta. Okay, simple itself. So yeah, so I think that's it for this lecture. Okay, so I hope you enjoyed Bode plots. I hope you learned something new from this Bode plots, which you have not learned before if you have already studied this chapter. So yeah, my error will be minus 1.58, and these are my answers. These are my answers. Like this is also one of my answers. Okay, so I will see you with a new chapter in controllers and compensators. So that will be also interesting. Like we'll understand the practical aspect behind it, why we use some type of controller to like change few parameters. Why do we use that? So before going directly into the controller compensator, I will give you a brief like overview of what happens if we add a pole, add a zero. We have already learned that, right? We have already learned that bit, but in the root locus we just learned about the stability and all those things, right? But time domain parameters we haven't learned, and during root locus we also didn't learn the frequency domain parameters. Like for a second order system I'm talking about, like the peak resonant and resonant frequency, all those things. So I will compare the peak resonant and resonant frequency when we add poles and zeros, something like that, in the next chapter, controller and compensator. So yeah, I hope you like this whole lecture series, and I will see you in the next lecture.